Making sense of QFT. Lecture 7. Greenberg-Schweber dressing. Let me remind you that in our last lecture we constructed the Hamiltonian HC of renormalized quantum electrodynamics. This Hamiltonian was composed of the non-interacting part H0, the original QED interaction V1, and two types of counterterms, R2 and W3. Our Hamiltonian described electrons, positrons, photons, and their interactions. For more generality, today we will add also protons and antiprotons to this list. We are doing it in order to have the opportunity to discuss such interesting systems as the hydrogen atom. The required modification is actually very simple. We just add a second term to the interaction density V1, where the electron-positron Dirac field is replaced by the proton-antiproton Dirac field. Of course, corresponding extra terms should be added to the counter terms R2 and W3. Another thing we learned yesterday was that all relevant operators in QED can be represented as sums of three distinct terms: physical, virtual, and renorm. In this table, I remind the meaning of the three operator types. First, there are virtual operators, which correspond to processes that cannot happen in nature due to violation of the energy conservation law. Yes, last time we had a detailed discussion of the first two terms, A dagger AC and A dagger C dagger A, which describe photon absorption and emission by a free electron. Let me also draw your attention to the third term in this list, A dagger, B dagger, C dagger. Here, B dagger is the positron creation operator. So this new term describes spontaneous creation of an electron-positron pair and a photon from vacuum. This is obviously forbidden. But the presence of such virtual operators in the S-matrix creates no problems because their contributions vanish. Then there are physical operators. They are distinguished by the property of having at least two particle annihilation operators and at least two particle creation operators. They provide non-zero contributions to the S-matrix and describe real scattering events. Finally, renorm operators have one annihilation operator and one creation operator of the same particle. Their presence in the S-matrix cannot be tolerated because they lead to a divergence. It is instructive to check the operator types in the QED interaction Hamiltonian. The original interaction V1 is finite and virtual. The second order counterterm R2 is divergent and renorm. And the third order counterterm W3 is divergent and virtual. The magic of renormalization is that after substituting this interaction into Dyson's formula for the S matrix, we find out that all renorm terms cancel out, and that physical terms appear which agree with experiment very well. It is interesting that the original interaction did not have physical terms at all. They appear in the S matrix as a result of products of virtual terms. Actually, it's not difficult to prove how the multiplication table of QED operators look like. Here, letters P, V, and R stand for physical, virtual, and renorm operators correspondingly. For example, in the general case, the product of two virtual operators is a sum of physical, virtual, and renorm contributions. This is how desirable physical scattering events make their way into the S-matrix. The bad news is that undesirable renorm terms also result from the product of virtual interactions. These are the renorm terms which we were trying to remove by the renormalization trick. Before proceeding further, let me formulate two important stability conditions. They follow immediately from basic experimental observation, and I believe that any realistic theory must satisfy them. The first one is the vacuum stability condition. It says that the vector of vacuum should not depend on time. Indeed, there are no particles, nothing in the vacuum. So nothing can happen there, and we can expect the absence of any measurable time dependence. As a consequence, the vacuum state must be an eigenstate of the total Hamiltonian with energy zero. The second one is the particle stability condition. It says that single stable particles, such as electrons, protons, and photons, should remain as one particle states at all times. Of course, we know about existence of unstable particles such as neutrons, pions, etc., but we do not consider them in our simple version of QED. In other words, the particle stability condition says that one particle states always remain within the one particle sector of the Fock space. This is equivalent to saying that the one particle sector is invariant with respect to the full interacting Hamiltonian. Let us now see how these stability conditions are satisfied by the components of the QED Hamiltonian. Obviously, the non-interacting Hamiltonian obeys both these conditions. However, this is not true for the renormalized interaction operator VC. For example, the presence of the term A dagger, B dagger, C dagger means that three particles can be created from the vacuum. So the vacuum state is not stable. The particle stability condition is violated as well. By acting on a one electron state, the interaction A dagger, C dagger A will create a new photon, thus forcing the state vector to leave the one particle sector. Of course, this transition cannot be permanent because it violates the energy conservation law, but our stability condition forbids such events from happening even for a short time. It is not difficult to notice that the bad actors who violate the stability conditions are virtual interactions. Perhaps it would be better to have a theory without virtual terms. Yes, but this is not possible if we work within the realm of quantum field theories. We already mentioned that QFT interactions always take the form of products of quantum fields, and that each quantum field is a superposition of particle creation and annihilation operators. Here is an example in which interaction is a product of 4 quantum fields of some abstract particle alpha. In this product, even after normal ordering, we inevitably find a term with all creation operators. This term destabilizes the vacuum. There is also a term with one annihilation operator. It destabilizes one particle states. The situation is quite different when we turn our attention to physical interactions. They do satisfy both stability conditions because they always have 2 annihilation operators on the right. At least 2 annihilation operators on the right. So physical operators yield 0 when acting on 0 particle and 1 particle states. This means that physical interaction acts only when there are 2 or more particles. This simple requirement is intuitively very satisfying. Thus, we conclude that the stability conditions would be satisfied automatically if the interaction had purely physical form. This idea was the essence of the dressed particle approach to QFT formulated by Greenberg and Schweber in 1958. Basically, they suggested to reformulate quantum field theory in such a way that virtual and renorm interactions are absent and only physical interactions are present in the Hamiltonian. The benefits of such reformulation are obvious. First, interactions in the Hamiltonian will correspond to real physical processes. Second, the vacuum and particle stability conditions will be satisfied. And third, from the multiplication table, it's clear that the product of 2 or more physical terms is always physical. This guarantees that bad renormed terms will not appear in the S-matrix. Then there will be no need in mass renormalization, and hopefully we may avoid the charge renormalization as well. However, the above plan raises a couple of concerns. First, what right do we have to change the interaction Hamiltonian of QED? But we can answer that this interaction was utterly unphysical. It had only troublesome virtual and renormed terms. Moreover, though, the counterterms were divergent. So we have a good incentive for trying to modify this interaction. Another question. The S-matrix of renormalized QED is extremely accurate. If we change the Hamiltonian, then we risk to destroy this agreement with experiment. Can we make our change without affecting the S-matrix? And the answer is yes, we can do that. And this is a great achievement of the dressed theory. If the new dressed Hamiltonian is obtained as a unitary transform of the old one, then the new dressed Hamiltonian HD has the same energy spectrum as the old one, and S matrices calculated with these two Hamiltonians coincide as well. As we already established, all verifiable predictions of QED are contained in its S matrix. And since our transformation preserves the S matrix, we have a guarantee that the dressed theory will have the same good agreement with experiment as the renormalized QED. The next few slides are going to be rather technical. I would like to explain how we are going to construct the dressing transformation and what the transformed Hamiltonian will look like. First, according to our plan, we apply unitary dressing transformation to the Hamiltonian HC with counterterms. The transformation operator is written here in the exponential notation with Xi being the Hermitian generator. Then we convert this action to the familiar series. And next, we represent the dressing generator Xi as a perturbation series as well. Substitute in 217 and collect terms of equal perturbation order. Now we are going to solve this system of coupled equations. The unknowns are operators Xi1, Xi2, and so on. Our goal is to select these operators in such a way that operators on the left-hand side become purely physical. Let's see how it works in the first perturbation order. The term V1 on the right-hand side is purely virtual, so Xi1 is selected to cancel this unwanted term exactly. Then the first order dressed interaction is zero. In the second order, we have a more complicated equation. The operator Xi1 was obtained from the previous step, and all other operators on the right-hand side are known components of the QED Hamiltonian. The only exception is Xi2, which we are going to obtain. So we choose Xi2 to cancel all virtual terms on the right-hand side. And it is remarkable that renorm terms, in particular R2, cancel out automatically without any special efforts on our part. As a result, we obtain a physical operator V2D as desired. We can execute the same plan in higher orders and obtain dressed interaction as a perturbation series, where all terms are physical, well-defined, and finite. You may ask, what about relativistic invariance? Indeed, how are we going to make sure that our new Hamiltonian satisfied the required Poincare commutators? The solution is rather simple. First, we have to select our dressing generator invariant with respect to translations and rotations. This actually doesn't require much efforts. Second, we should apply this transformation to all 10 Poincare generators of the renormalized QED. Momentum and angular momentum will remain unchanged due to our choice of Xi. And we already discussed the transformation of the Hamiltonian. A well-known property of unitary transformation is that they preserve commutation relations. So if the renormalized QED was relativistically invariant, then our 10 new generators will have the required Poincare commutators as well. Let us now see which dressed Hamiltonian we will get as a result of our efforts. First, we note that this operator cannot be obtained in a closed form. The best we can do is to write a perturbation expansion and evaluate few low-order terms, but for most physical applications, these results are perfectly sufficient. In the zeroth order, we have our familiar free particle Hamiltonian, which is the sum of relativistic kinetic energies of non-interacting particles. There are many second-order interaction terms, but I'll mention just few of them. For example, the term A dagger B dagger AB describes the electron-positron interaction. In particular, it's responsible for the binding in the positronium. Then the term A dagger C dagger AC describes interaction between electrons and photons. C dagger AB destroys an electron-positron pair and creates two photons. So this is the electron-positron annihilation. In the third order, the term A dagger B dagger C dagger AB destroys electron and positron and then creates this pair of particles back plus a photon. This interaction should be able to describe photon emission in electron-positron collisions, as well as the spontaneous radiative transition in the positronium. A dagger AAC tells us how a photon can be absorbed in electron-electron collisions. Among many fourth-order interaction terms, we will pay special attention to the A dagger B dagger AB. This is a very small correction to the electron-positron interaction whose main part was described in the second order. Among other things, this term plays a role in the anomalous magnetic moment and in the positronium lamp shift. We included in our theory also protons whose creation and annihilation operators are d dagger and d. Therefore, we should also have a d dagger, a dagger, dA operator in the second order. It describes the electron-proton interaction. And if we limit ourselves to the electron-proton sector of the Fock space, apply a low-velocity approximation, and switch to the position representation, we will obtain an approximate interaction potential between the two particles. This potential is shown here, and remarkably it coincides with the so-called Darwin-Braid potential, which was derived much earlier from completely different principles. All terms in these potentials are well known and well understood. The strongest part is the Coulomb potential. Then there is a contact interaction. As it is proportional to the delta function, this interaction is extremely short range, so it has no effect in classical electrodynamics. The next one is Darwin's or magnetic potential, which depends not only on particle positions, but also on their momenta or velocities. There are also terms in which particle momenta interact with their spins. They are called spin-orbit terms. And finally, there are spin-spin interactions. It is well known that the Darwin-Braid Hamiltonian describes very well all electromagnetic phenomena which do not involve radiation. So it has a potential to substitute the field-based Maxwell theory. Moreover, it describes energy spectra of atoms with relativistic precision. Here is how this potential works in the classical example of the hydrogen atom. Let us first leave only its strongest Coulomb part in the Schrödinger equation and focus on two lowest energy levels of hydrogen: the ground state 1s and the degenerate excited state composed of 2s and 2p orbitals. Next, by adding contact magnetic and spin orbit terms, we will see how the so-called fine structure becomes resolved. The 2p 3/2 level splits from the degenerate group of 2s 1/2 and 2p 1/2. If we now add to the mix the third and fourth order contributions to the Dresd potential, we will obtain the so-called lamp shift, which splits the 2p 1/2 and 2s 1/2 levels. Finally, the superfine structure is revealed after we take into account the spin-spin interaction of the proton and electron. As you can see, the Dresd theory in the first order provides a very good approximation to the experimental atomic spectra. Let me now summarize the conclusions. By using the Greenberg-Schweber dressing idea, we transformed renormalized QED in a new theory where particles are the main ingredients. In contrast to bare particles of the original QED, our physical particles lack self-interaction. So there is no need for renormalization. The masses and charges used in the Dresd Hamiltonian are exactly the ones from physics handbooks. The Hamiltonian of the Dresd particle theory is finite. The theory is relativistically invariant. So far, interaction operators have been calculated up to the fourth order, but these derivations can be extended to higher orders without difficulties. These interactions have the form of potentials that depend on positions and velocities of the particles. Processes involving particle creation and annihilation can be treated as well. It is remarkable that the Dresd theory S-matrix is exactly the same as the S-matrix of the renormalized QED. So all good theoretical predictions of the latter are reproduced. But the real advantage of the new theory is that it can go beyond the S-matrix. In particular, it can calculate the time evolution of state vectors and observables, as well as wave functions of bound states. To get these wave functions, the Dresd Hamiltonian can be projected approximately, of course, on a selected few particle sector of the Fock space and diagonalized there. So the problem of bound states is solved just as easily as in the non-relativistic quantum mechanics. In the next lecture, we will discuss possible experimental tests of the Dresd QED and how this theory relates to Einstein's special relativity. See you next time. Thank you.